Yeah, hello students. Welcome to Unit 2. This is a syllabus. Linear regression, that is part 1. Linear 2 class classification, that is the second part of the Unit 2. In the part 1, we are going to discuss about least square regression. Least square or linear regression, especially linear regression only we are going to do. Because in probability and statistics, you studied both the linear and non-linear regression with help of the method of least squares. Here, we are going to discuss only least squares. Now, apart from that one, least absolute deviations that we are discussing, in between there is only little difference is in least square regression, what you are checking is we are finding the squares of the errors. Here absolute value of the error only we will check. That's only the difference in first part. Here at this time I would like to discuss only these the two topics for the first part. Okay, let us go to that. So probably principle of least squares you might have studied. In this one, the couple of points will be given: x1 y1 x2 y2 and so on, x and y1, and we were asked to compute the given function y equals to f of x. The f of x can be anything. Here, f of x can be anything. F of x can be a what I mean to say that a straight line or a parabola, and geometrical or exponential curve, anything it may be. It can be anything. So here, for example, if I go with the linear curve, if I go with the linear curve y equal to mx plus c. In this one, what exactly we are trying to check is let me okay. So this here, suppose here I have a couple of points like x1 y1 x2 y2 and so on, x and yn. Graphically, if you plot this, they can be here. Let it be x1 is at here, x1 y1, x2 y2, x3 y3, x4 y4, x6 and so on, x and yn, like this. Here you are asked to compute a straight line. So the straight line can be right here. The straight line can be represented here. Okay, this may be one. In this one, some of the points may be above the line or some of the points may be below the line. This one I need to adjust in such a way that this one I need to adjust in such a way that here okay, may I can choose the point like a straight line like this, or I may choose a straight line like this, or why like this, why can't another any other way? Yeah, even I may go like this. Like this, infinitely many possibilities are there. Infinitely many possibilities are there. Out of this, I need to figure out one only one straight line or parabola or exponential curve or geometric curve. So how to figure out this one is what the major task in between is. Okay, imagine this is the one which we required. So here what I'm checking is the distance from here to here. I'm identifying the distance, this exactly, and that one, like this. So this distance is known as error e1, e2, e3, e4, e5, e6 and en. So here what I'm checking is e1 square plus e2 square plus e3 square and so on plus en square, which is a minimum, which is a minimum. So that means here I checked the sum of the squares of the errors is a minimum. So first of all, what do you mean the error here? Actually this point is x1 y1, but this is, let it be y equals to y dash. So at this particular point, this difference at this particular point, y1 dash minus y1, that is known as error, or I can say that here y minus ax1 plus b. This is error. Now it's a square of the error I need to compute. Why the square of the error is need to compute? So let me explain you that practically. Suppose, imagine this is minus 2, for example. This is uh, since it is above, let it be taken as plus 2. This is plus 3. This is minus 1. This is minus 3. This is 0. This is plus 3. Let it be this is minus 2, for example. If we add those errors, 2 plus 3 plus 3, here minus 1 plus 3 plus 0 plus this minus is 2. What is the meaning of that here? Here 8 minus 6 equals to 2. So the error is, so it is not, sometimes what it may happen is, for example, this is one more point is here, which is minus 2, for example. Then it could be here minus 2. So error 8 minus 8 is 0. So no error. Is it the meaning of that one is the required line is passing through all the points, but unfortunately we are identifying some errors. We are identifying some errors, but if I sum that the errors, I found it is 0. So that's the reason I'm not going to take directly the errors. Instead of the errors, I may take sum of the squares of the error. The errors, the sum should be in such a way that it is minimized. It is as minimum as possible. It is as minimum as possible. Okay. So let me show you some numerical example to so that you may understand the same. So this thing is the whatever that I explained here. That is error is y1 minus f of x1. Error 2 is y2 minus f of x2. Error 3 is y3 minus f of x3, and so on. And the final principle is sum of the squares of the errors is minimum. Why the sum of the squares is error? Why the sum of the squares is squares is taken is here. Sum of the errors will be positive, sum of the negative. If I find the total of the errors is added, initially some negative and some positive errors may cancel, and in some cases the sum of the errors may be 0, which leads to the false result. We thought that if the error is 0 means that is exactly apt to the given points, but unfortunately here the points are not exactly all the point at the given curve is not passing through all the points, so that makes the error. That's the reason we are choosing some of the squares of the error in some cases. And second point, I mean second topic in this one is here I have chosen some of the squares. There some of the absolute values I may choose. So absolute value means it will be even all the negative values will turn to positive value. Then that minimum, that error is to be minimum. Some of those deviations of the errors is a minimum. That is also the next kind. So to calculate that one, for example, if I go with the straight line y equal to x plus b, y equal to x plus b, the normal equations which you already dealt in probability and statistics is like this. So where a equal to y equal to ax plus by, y equal to a plus bx, that is a required straight line. Then to compute that here x and y values will be given. Okay, like this. X and y values will be given to you. X and y values will be given to you, and for that you need to compute the a and b. To compute a and b, I wanted to create two normal equations in terms of a and b. That's what. For that one, here I'm using least squares, or it's nothing but gradient method. Gradient means here simply differentiating with respect to that and equating to 0. So why equating to 0? I'm choosing that stationary points here. So whether it is a minimum or maximum, at that uh, what you may call the, in first unit we learned that at stationary points the gradient would be 0. That is only the reason I'm choosing that station at the stationary point the behavior of the function may be minimum, may be maximum, may be saddle in nature. I believe that it is minimum in nature. I believe that I'm thinking that it is a minimum in nature, and I'm choosing that. So that's the reason here unknowns are a and b, because x and y are given in the problem. So with respect to A and with respect to B, we are computing the derivatives and equating to 0 so that I may get two normal equations in terms of A and B. Why two normal equations? Because with respect to A, with respect to B, I choose them. With respect to A, one equation, with respect to one equation later onwards, I compute these values and substitute in this, I'll get the solution of that. This is the numerical example for that, x values and y values. As per the normal equations here, sigma xy equal to a sigma x plus b sigma x square. Sigma xy, this is uh, and another equation is sigma y equal to a into sigma x. This is another equation. Sigma y equal to n into a plus b into sigma x. So which are the values we don't know, that we are computing. So if I go with this as the first equation, let it be this is the first equation. In that one, sigma y I don't know, but I can compute sigma y. N means count the values 1, 2, 3, 4, 5 like that. So n values are 5. Sigma x means finding the sum of the sigma x. From the second equation, sigma xy I do not have, but I can compute that one. And sigma x already I have. Sigma x square I do not have, so I may compute that. Computing that, and I may find a and b values. A and b values. So don't expect that it is satisfying 100%. For example, here, if I substitute 0 here, if I substitute 0 x is equal to, then y is supposed to be 1. But in this one, if I find x is equal to 0, y 1, okay, fine. X is equals to 2, x is equal to 1 if I plug, then y equals to 1.9 plus 1, 2.9. Oh, very good. This data is apt. And 2, if I plug in 2 here, 2 times 1.9, it is 3.8, 3.8 plus 1, 4.8. So 4.8. Oh, so this is like that, but don't expect that it may be possible, it may not be possible for all the values here. Okay, similarly, if I see this the same way, x values and y values, at here I may compute the values of, this is y equal to 13.6x. If I plug 1, x is equal to 1, I may get here y equal to 13.6, but here it is 14. Y equal to 2, if I substitute 13.6 into 2, so here 26, 27.2, it is 27. So some of the points may be above, some of the points may be below, but here we are adjusting the line in such a way that error should be minimum. Now back to this, see this here. Now supervised learning problem. What do you mean the supervised learning problem means here? For a given x values means inputs and outputs both are known to you. That is known as supervised. Supervised in machine learning, supervised learning. Supervised learning means when you know the outputs also. Here the inputs are x values, outputs are y values. Is called linear regression. And the fitting of the representative of line in, suppose in one dimensional, it look like this. In one dimension it is look like this. In multi-dimensional it look like a line will be turned to the hyperplane that we have seen in earlier classes. Okay, so here, so fitting the representative line in one dimensional, in case of higher dimensional it could be turned to the hyperplane. Then regression may be performed for a variety of the reasons. Why we are using the regression is to produce so-called trend line. We'll call it as a trend line or approximate line to this one. More generally, as we see later, a curve, simply a curve. Here, for example, to understand that one, I used a straight line that can be used to visualize or summarize the given data. For here, as we see for this data, how can you visualize the curve can be expected. For here, hardly have only 5 points, but in real time real-time data, it consists of the millions and billions of the data. By that time it is highly difficult to visualize by checking the manually. So by that time I may depend on this concept. Okay, so in this description here, we'll describe variety of the various ways of the designing appropriate cost function. What does cost function, appropriate cost function? So the cost function here, it is, this is difference. This is called the cost function. yi minus f of xi. Why it was written here? Okay. So, or simply yi minus f of xi. Okay. Okay. Here it is. You can see that here. This is a cost function. Yn minus f of xn as a pointwise. As a pointwise. So this is cost function for regression, including discussion of the least squares, least absolute cost. In the problem, whatever we discussed is it is about least squares. Now least absolute deviations means what I said is here this difference, to this difference I used the absolute value. This difference I used the absolute value. Okay. Let me write down here. Okay. Earlier we write here y equals to f of x for n different points. Cost function I can say that y minus or yn minus f of xn. This is the cost function, and this y and the final y is a different. So that's the reason don't expect that this y and then this y are the same. So this difference whole square. That one in case of least squares. Whereas absolute value means yn minus f of xn. Absolute value I may check. That's it. That's only the difference here about least squares and least absolute deviation cost. Nothing more than that. Now let me go one by one. So here least squares linear regression. Least square linear regression. Linear means the expected value is, here we may get doubt that y equals to ax plus b, it is a straight line, and y equals to a plus bx plus cx square, it is a parabola. Can I say that it is a linear regression? Yes. How do you know that linear regression? Because here the variables x and y values are given. The variables are a and b only in this case. So those degrees are 1. That makes a sense that it is a linear. That's what. Okay. So non-linear means here I may get y equal to a times b power x, or y equals to a times e power bx. So here it may not be linear. So non-linear regression means this you studied. Linear regression means this you studied here. Okay. In terms of A, B, C, I'm talking about in terms of A, B, C. But in terms of the lines, this is only the linear. These three are non-linear. In terms of the line, in terms of the X, Y, these three are non-linear. This is only the linear. But in terms of A, B, these two are linear. This is a non-linear. Right. Okay. So here we in this we formally introduce a linear regression, or the fitting representing a line. Line in case of only x and y are inputs. Hyperplane in case of y and multiple inputs or higher dimensions, I can say that. And we walk through the popular least square cost that we come across just now. Here these are the points, for example x1, y1, x2, y2 and so on, xp, yp. where if I choose a general point, this one I may represent the compact form xp comma yp from the p equal to 1 to capital P, or you may choose any one. In this one, xp yp denote the input. This is input, this is the output, this is output. So since output is known, that's the reason it is known as supervised. Supervised. Okay. Now, since it is in case of multi-dimension, how it will look like is xp. It is a column vector always xp and y. The corresponding yp also the similar to that. So here, suppose when it is vector is when our multi output. For example, here y equal to a plus bx. In this case, only one output, one input. Here, one input. This input. This output. Sometimes here, what it may happen is y equals to a plus b x1 plus c x2 plus d x3. In case here 1, 2, 3, these are the inputs. That means multi input, and this is only the one output. So whenever there is only single output, then it is known as a scalar. Whereas multi output, for example, y1 plus y2 equals to a plus bx1 plus cx2 plus dx3 plus ex4. In this case, I may say that this is not a scalar, this is a vector. Okay, that makes the difference here. So that's a here each yp is a scalar valued. Reason is only one output I'm expecting. If it is expecting more than that, then it may be different. Okay, geometrically speaking, linear regression problem is one of the fitting a hyperplane of a scalar scattered positions of n plus 1 dimensional space. How it is n plus 1 dimensional space? This is n plus y is included in this one. Y is included. That makes a sense here. The simplest one is n equal to 1. If I go with n equal to 1 means 2 dimensional. How the 2 dimensional here? If n equal to 1 is 2 dimensional. The 2D is one is x, another one is y. That makes a sense. So this is W0 plus XP W1 is equivalent to YP. Is equivalent to YP, where P equals to 1 to capital P. 1 to capital P is for his convenience. If you want, you can put you may put as per your convenience. Let it be N also or W also, something else. Okay. Now, in case of the one input, that one input is XP. Suppose here I have multiple inputs x1, x2p, and so on xnp. Whenever it is a multi-dimensional, then dealing with n-dimensional input, then we have in this always the okay, y equals to a plus bx or y equal to a plus bx plus cx square. In these two cases, this is known as bias term. Bias term. Bias in the sense to understand in easier way. To understand that in easier way, while in olden days, simple balance, while to purchase anything, it will be with help of this simple balance. Here, suppose 1 kg stone, it may be here or it may be here. To make this from here to here, I am adding something more. That something which you are adding is known as a bias term. The something which we are adding. In Telugu, that is known as kosaru. That is. So this is bias term. So which will be which will be correction. I can say that it is use it for the correction. Okay. So now here, then remaining W1, W2, W3 and so on Wn are feature touching weights. So that means how many dimensions that you are using, they are known as simply features. Features means, for your understanding purpose, suppose if I want to purchase a house, the features would be one is location, next area. In the location means land cost, I can say that land cost. Third, amenities provided. Fourth, your customized options, like which interior design, what are the facilities that you required for your interior purpose, and whatnot. So these are all the input features. That is what the meaning of the feature touching weights. In this one, to make its cost effective, you may check this, or you may check this. You can minimize the amenities. Okay, you can minimize the amenities, and you may choose, instead of 3 bedroom flat, I can go with a 2 bedroom flat, like that. These are the feature. So the only weight is not touching the feature is a bias. So bias is not influenced by these values. Bias is only correction factor, I can say that, for your understanding purpose. The linear relationship would be like this. So xp equals to here I can write 1. 1 is here w0, this is w1, w2, and so on wn. That is what here it is. So where p1, p equal to 1, 2, 3, and so on, the placing all parameters in the single column vector w. If a single column vector w, I may get this. So in case of the two input, so this one input, this one output, this is a bias vector, and this is one feature, single feature only. So this is a bias vector, two features. Okay, this is about that. In case of the, this is here, it is only one dimension, it is two dimensional. In case of two dimensional, the straight line will be turned to the hyperplane. This is hyperplane here. Okay, so we may write this here, y equals to x transpose w, y equal to x transpose w. So here y equals to x transpose w, I can write here x transpose is already we mentioned here, it is this 1 x1p, x2p, and so on xnp, and transpose, and w1, w0, w1, and so on wn. All together I can write here, since it is a transpose means column vector would be turned to row vector, then I can write here 1 times w0 plus x1p times w1, x2 times x2p times w2, and so on xnp wn. That's what this is y. So it will be now turned to 1 by 1. 1 by 1 means it is a scalar. That's the reason it is known as scalar. That's what. So the scalar is somewhere given here. Each output y is a scalar valued is turned like that. Okay. And now least square cost function. How the least square cost function means? Simply here what I am checking is the difference between the y and means here, see, at each and every point the difference, this is y value, so this difference is the cost function. This difference is as minimum as possible. This difference is as minimum as possible. Even in the multi-dimension also the same way. This difference as minimum as possible. Okay. So least square cost function for a given set of parameters. W is the cost function. Okay. Okay. least square. For a given set of parameters, the vector w is the cost function, computes the total squared error. Total squared error means simply sum of the squares, total sum. So what is our target is, mm, the best fitting hyperplane is the one whose parameters minimize this error, minimize the error. So sum of the squares of the errors, e1 square plus e2 square plus e3 square and so on plus en square, this is minimum. That is what. So focusing just on the pth, so focusing on just pth approximation, we ideally want to be xp transpose to be close to the as much as close to the yp, and equivalent error difference is, this is what, x transpose w minus y, this is as small as possible that we studied. So here I may adjust this one in such a way that either in this way or in this way, so that the error should be minimized in case of one input one output. Here in case of multi input one output, then this would be turned to squares, this would be turned to a square. That's what. So left panel is a two-dimensional data set along with the line fit to the data using least square framework, which aims to be recovering linear model, minimizes the least square length solid bars only, whereas right side blue squares, because it is having solid block errors, it is a cost function is called least square because it allows us to determine the set of parameters whose corresponding line is a minimum, the sum of these squares. This is what yp minus the function is x transpose w. That difference it is considered as error. That error square should be minimum. That means finally it should be minimum. So for that one, what I'm taking is average of this, average of this one is taken here. So the both the negative and positive errors will be same magnitude. That's what we discussed. So as the point wise cost function, this is at a point p, I'm talking about a point p, the cost wise measures the errors of the model. Now we all want the all p such values to be small, and simultaneously we can take the average, we can take the average over the entire data set. In mathematics we won't take this average, of course it is inbuilt, but it is inbuilt, we are not using it because y equals to a plus bx, then the normal equations are sigma y equals to an plus b sigma x, and sigma xy equals to a sigma x plus b sigma x square. In this one I haven't taken any average, but here we'll take average. That is okay then. So like that I may take. So notice that the larger the least square becomes, larger the squared error. So if this value is, for example, 1 square plus 3 square plus 4 square, maybe minus or plus, it doesn't make any difference, plus 5 square for example, the error would be 1 square plus 9 plus 16 plus 25. So the value would be 10, 10 plus 40, 10 plus 40, 50, 51. This is, suppose if I adjusted the error up to this, suppose here I make a error to the minus 1, for example, minus 1 means it will be turned to 0, 0 square it will be turned to 2 square, it will be turned to minus 1 means it is minus 5 whole square, it is plus 4 square. What I may get, let us see that, 0 plus 4 plus 25 plus 16. So here I make it for 20, 20 plus 25, 45. Suppose if I reduce further, earlier from here to here minus 1 shift. Again minus 1 shift means minus 1 whole square plus 2 square, sorry, minus 1 square plus minus 6 whole square plus 3 square. What I make it here, 1 plus 1 plus 36 plus 9. So I make it here the 46, 36, 46, 47. See that here 45, 46, 51 like that. So depend upon the situation whether I may increase or I may decrease. Suppose even if I add this, even if I add 1, why I subtract y, even you can add 1 also. So in this way I am going to check whether it is a minimum or maximum in this. Okay, okay, in this case I may check whether it is a maximum or a minimum, that is. Okay, so here the least square should be minimized. So finally, this is the cost function I may define here. Actually, y equals to x transpose w. This is now the difference is whether it is x transpose w minus y or y minus x transpose w. Both are same here because I am not going to take this one directly. I am taking its square. So whether it is positive or negative, it doesn't make any difference. So using tools for local optimizations, that is detailed. So local optimization means here I'm going to differentiate. That's what here. Okay. So this is what, these are the tools with respect to bias function and with respect to input parameters. I may differentiate and I may conclude this value. I may compute this normal equations. Now it is explained with help of some problem. It is like that. You can go through it. Python implementation is also explained with the help of a program. You please go through it. This is what we studied this one as a plus bx. This is this one we represented because w is equal to w1 w2, w equal to w0 w1 like that. In case of multi-dimension it could be, in case of multi-dimension it could be like this. And the Python implementation is explained here. You can come across linear regression. Finally, what you are doing here, this is what the gradient. So here I am differentiating this one with respect to the gradient since it is a square. Okay, what is the g of w equals to, g of w equal to 1 by p sigma x transpose x0 transpose p w minus yp whole square. Gradient g of w equals to, that I am trying with help of x, this w, input parameters. Input parameters are xp. So if I try this one with respect to this, I may write this one here. It is in the form of x square. So d by dx of x square will be 2x. That's the reason 2 by p sigma x transpose p w minus yp times differentiation of this one, dou by dou w of xp transpose w minus yp. So with respect to w, it is 0. This is the leftover. That's the reason xp transpose we wrote here. Okay. Why the transpose were not taken? That if you expand that one equation, you may get it. Similarly, with respect to this one is further simplified here. This one is further simplified here. Since this is equal to 0, we make this one to equal to 0. Then I can write here 0 equals to, see this here, 2 by p sigma p equal to 1 to capital P xp transpose w minus yp, that is equal to 0. If product of something equal to 0 means the only option is either this to be 0 or this part to be 0. So it may not be 0, because 0 means numerator should be 0, because numerator is 2, so it cannot be 0, only this part will be 0. That makes here sigma p equal to 1 to capital P xp and xp transpose w minus xp yp. This is equal to 0. Furthermore I can write here sigma p equal to 1 to P xp xp transpose w equal to sigma p equal to 1 to capital P xp yp. This is what we wrote here. Hope it is clear to you. Similarly, least absolute deviations means we are having only absolute values instead of this. See the difference here. In g of w earlier we wrote some of the squares are there. Now we are taking absolute value of this. That's only the difference. Rest of the things are as it is. So here average, then if I differentiate that with respect to w, I may get similar that. And here if I find the difference, which is the best one, it is explained with help of the graph. It may not be common to all, it may be different from the problem to problem. So that's the reason you need to learn both. So far you please check this one. Next topic, regression quality metrics will be explained in a separate topic, separate lecture. Till that, keep practice.